So welcome students. So in this question you're given that R is a relation defined on square matrices of order 3, and the definition of R is R relates A and B if A can be written as some P inverse BP for some invertible matrix P. So if this can be done, then A and B are related to one another. So the first statement is that R is equivalence. The second statement is Mn whole inverse is equal to N inverse into M inverse for all N and M invertible matrices of order 3 by 3. So straightforwardly statement 2 is true because statement 2 is a theoretical statement. Mn whole inverse will be N inverse into M inverse. This is called reversal rule, reversal law of inverses. So this is true, there is no doubt about it. What you need to check is statement 1. So let us see whether statement 1 is true or not. So R is equivalent, so I need to check reflexivity, symmetry and transitivity. So first let me check reflexivity. So let me take two identical matrices A. Will these two be always related by the relation R? Yes, because A can be written as I inverse AI, right? I inverse AI will always be equal to A. So you have a matrix P which is equal to I, which is invertible. So that I can write A is equal to I inverse AI. So I'll always have this matrix I for corresponding to A. Hence, A and A are always related to one another. Hence, the relation is reflexive. Second, so let me check symmetry. So in symmetry, I'll take let A comma B be related. So let A comma B be related. That means A should be equal to some P inverse BP, right? So if these two are related, that implies A should be equal to some P inverse BP. So because P is an invertible matrix, so I can multiply this with P. I can uniformly multiply this with P. So PA will be equal to BP. This implies PA, P inverse will be equal to B. P into P inverse is I. So B can be written as, this implies B can be written as P times A P inverse. That is nothing but P inverse whole inverse A times P inverse. So if you take P inverse as my new matrix Q, that is Q inverse AQ. So B can also be written as some matrix inverse AQ, where Q is an invertible matrix, because if P is an invertible matrix, P inverse will also be an invertible matrix. So if I can write A as P inverse BP, I can write B as Q inverse AQ. Hence, B and A are also related. B comma A also belongs to R. That means the relation is symmetric also. So if you go for transitivity, if A comma B and B comma C belongs to R, this implies A is equal to some P inverse BP and B is equal to some Q inverse, right? Some Q inverse CQ. So now using these two, can I write A as some matrix inverse C some other matrix? So that's what you need to analyze. So A is equal to P inverse BP, B is equal to Q inverse CQ. So this implies, so can I write A as P inverse, B is nothing but Q inverse CQ, that is Q inverse CQ times P, right? So this is equal to, so P inverse Q inverse, can it be written as QP whole inverse C QP? So if you take QP as a matrix R, so this can be written as some R inverse CR. That is, A can be written as some matrix inverse CR, where R and R inverse are invertible matrices, because Q and P are invertible matrices. So Q into P will also be an invertible matrix. So A comma C also belongs to the relation R, right? So this R is different, this R is different. Make sure of note that. So if A comma B and B comma C belongs to the relation, A comma C also belongs to this relation. Hence the relation is transitive also. Hence I can say that R is an equivalence relation. Now Mn whole inverse is equal to N inverse into M inverse. I have used this relation. As you can see, I have used this relation in proving that my relation is transitive. So in one way, S1 and S2 are both true, and S2 can be thought of as the reason for S1 to be true. Because if this is not valid, I cannot write P inverse into Q inverse as QP whole inverse. So I would not have been able to show the transitiveness of this relation. Hence S1 and S2 are true, and S2 is the correct reason for S1. That should be the answer to this question. Thank you.